Welcome to day 2. We're going to be drawing some graphs of exponential functions. We're going to take these 5 functions, f, g, h, m, and p, and we're going to draw them on this grid. But first I'm going to look at how they look at GeoGebra.org, and it'll be a lot easier to tell some differences between all of them. So I'm going to go to that website. So GeoGebra.org is a nice little website. We're going to go in here and we're going to start looking how we're going to do some graphs. So I'm going to go to the graphing calculator part, and you see we get this nice little grid, and we have this part on the left here where we could put in our functions that we want. We have a nice little tablet here, so like the first one we could put in was 3 raised to the x, and there's the first graph that we're going to do. So I'm going to put all 5 of them into the calculator, and look what happens when I hit equal. Right now it even says f of x. So there's the first one. I'm going to put the other 4 in. So you see I put all 5 of these on the one grid, and what's really like about GeoGebra, these little, I play with the colors, I can play with the thickness of the lines, I can put the labels on here, but I also could turn off graphs if I want by hitting the little these little circles. See, now I just have f of x. That's the blue one. I could add on g of x, the red one, h of x, the black one, m of x, the pink one, and p of x, the purplish one. And we're going to look at the difference. We're going to see what they have in common and how they differ. I think right now we could tell that they definitely have something in common. They all go through the point 0, 1. They all have different shapes. 3 of them are growing because their b value is bigger than 1, and 2 of them are decaying because their b value is less than 1, and they all have different steepness, it seems like. Maybe the purple and the red have about the same steepness, but the blue is definitely steeper than the red, which is steeper than the black, and we're going to talk all about that on the graph. I'm going to go back to the handwritten notes, but I just want to see what GeoGebra looks like. You could use this when you do homework. We're actually going to use this when we do our writing assignment next week of the transformation of mixture functions, because you could use this website to do your transformations for you. So obviously the GeoGebra version of these graphs are a lot better than what I can draw, but what do they have in common? They all go through the point 0, 1. Their domain and range would be the same, and they all have a horizontal asymptote of y is equal to 0. Where they differ, definitely some are growing. That's when the b values are bigger than 1. Some decay. That's when the b value is smaller than 1. And the steepness of the curve is where they definitely differ. So what effect does b have? That b value, that the number under the exponent x, that is the steepness of the curve. Obviously we have growth when b is bigger than 1. We have decay when b is less than 1. But here's the big idea. The closer b is to the number 1, the flatter the graph. If b was equal to 1 and we did 1 at x, it would be a horizontal line. There would be no curvature to the graph. But if b gets a little bit bigger than 1 or a little bit smaller than 1, it curves up a little or it curves down a little bit. The farther b gets away from 1, the more curvature or steepness you would get to the graph. So a times b to the x is always our parent function, and if b is bigger than 1, we're going to have a growth graph. It's going to go something like this. This point right here is the y-intercept, and that is always going to be a. So the y-intercept is 0, a. My domain is all real numbers. My range is 0 to infinity because there is a horizontal asymptote of y equals 0. Now both ends don't have to level off, but one does. HA of y equals 0. the x-intercept, there is none. And the limits, x goes to infinity is the right side, and that side goes up to infinity, and x goes to negative infinity is the left side, and that levels off to 0. That's what we're looking at. Well, what if b is less than 1? Well, that's a decay graph, and it's going to be very similar to what we've done here, except it's going to be the other way around. It's going to go from, the other graph went from low side to high. This is going to go high to low. Still has a y-intercept of 0, comma a. My domain is still all real numbers. My range is still 0 to infinity. I still have an HA of y equals 0. Still no x-intercept. And my limit, well, now the right side levels off to 0 and the left side goes up to infinity. So that's basically what every graph that we're going to draw today is going to look like. This kind of curvature, either exponential growth or decay. So I'm going to look at my letters of my transformations, the capital A, the capital C, and the capital D. We're not going to do capital B. But I'm always going to look at y equals a times b to the x as my parent function. This is my basis, what we just did on the other page. This is what I'm going to try to graph first. So let's see. Capital A is actually part of that equation, but in general, it still is a vertical stretch or compression. And if A equals a negative, it's going to flip the x-axis. That's still the same thing we did before. But I'm going to use this idea of my parent, and I'm going to say my y-intercept is going to be 0, comma a on the parent. And then I could do some other points by plugging in numbers for x. So if I plug 1 in here, I would get a times b as another point. If I plug 2 in here, I would get a times b squared. If I went backwards and did negative 1, well, b to the negative 1 would be dividing by b, a over b. So the whole idea is that when I move to the right, I'm going to be multiplying by b, and when I move to the left, I'm going to be dividing by b. And these are other points on the graph to help me with my parent graph. The C is going to be a horizontal shifting, again by the opposite of what you see. And then finally, D is going to be a vertical shift by what you see, the D value. But its effect is that my horizontal asymptote is always going to be y is equal to D. That's going to be important to us because it's going to help me tell me where the graph level's off, and it's going to help with the range. So I see 3 letters here, A, C, and D, but I'm going to use y equals negative 6, 1/2 to the x as my parent. It already has the vertical stretch by 6 and the flip x already built into the parent, so I don't have to do them later. So some points on here are going to be 0, negative 6, 1 times negative 6 times a half would be negative 3, 2, and negative 3 times a half would be negative 1.5. So those would be points on the parent graph, which I'm going to draw right now in the gray. 0, negative 6. I can grab the color. 1, negative 3. 2, negative 1.5. And the parent always levels off. One side of this graph has to level off to 0 on the parent. So right now, that is my parent graph. Then I'm going to list my transformations. Well, plus 2 means left 2, and plus 3 means up 3. Not only is it up 3, y equals 3 is my HA. Y equals 3. So all these dots on this graph are going to go left 2, 1, 2, 1, 2, 3. And there we go. There's a dot here at negative 2, negative 3. Left 2, 1, 2, 1, 2, 3. I have another dot here at negative 1, 0. This one's going to be a little bit harder. Left 2, up 3, 1, 2, 3. I have a dot here at 0, 1.5. I'm going to draw the same shape that I drew earlier. And that is the graph of what I wanted to do. The domain is all round numbers. My range is from negative infinity because it got flipped to positive 3. Negative infinity is the left side. That goes down to negative infinity. And x goes infinity is the right side. And that levels off to 3. Okay, my parent is going to be y equals 4, 1.5 to the x. Already has a vertical stretch of 4 in it. I don't have to do it later. So some key points around this are 0, 4. Plug in 1, I get 6. Plug in 2, I get 9. 0, 4, 1, 6, 2, 9. And again, one side has to level off to 0. And there is the parent graph. So again, I see the letters A, C, and D. I don't have to redo the 4. That's already part of the original parent. Makes my life easier. And minus 3 is going to be right 3. And negative 5 means down 5. And that was it, down 5. I have my horizontal asymptote. My HA at y is equal to negative 5. Make it a little bit cleaner. So every single dot I have here, I have 3 of them here. They're going to go right 3, 1, 2, 3, down 5, 1, 2, 3, 4, 5. So I have a dot at 3, comma, negative 1. This dot here is going to go 1, 2, 3, 1, 2, 3, 4, 5. And that's at 4, 1. And this dot here at 2, 9 is going to be 1, 2, 3, 1, 2, 3, 4, 5. And that point here is at 5, comma, 4. We basically draw the same shapes I did earlier. And there's the new graph that I really wanted. Again, my domain is all round numbers. My range is now from negative 5 to infinity. My HA is y is equal to negative 5. The left side of the graph is leveling off to negative 5. And the right side of the graph is growing all the way up to infinity. So we could always use more practice writing equations. This a times b to the x. I gave 2 points. What's nice is that I gave you this point right here, 0, 2. And that's the a value, so I have y is equal to 2 times b to the x. Now I could plug in this point, 5 equals 2 times b to the negative 1. But b to the negative 1 really means 1 over b. So this is really 5 is equal to 2 over b. I can multiply by b on both sides, because I really don't want to work with the denominator. And I can divide by 5, and I get b is equal to 2/5. And that seems about right, because this is a decay function. My b value better be smaller than 1. So y is equal to 2/5. Here's the x. Is the equation of that graph. This one is definitely going to be more difficult because I do not give you the y-intercept, and I give you 2 ordered pairs here that have fractions in them. So when I see I don't have the y-intercept, we need to do a system. I'm going to use the higher x first. 9 over 2 is equal to a times b squared over, I'll use the second point, 8 over 9 is equal to a times b to the negative 2. When you divide, you need to subtract my exponents here. Don't add them, subtract them. And you get, well, the a's cancel out, and you're going to get b to the 4th. 2 minus a negative 2 is going to be 4. I have to kind of divide these fractions, and I get 81 over 16, or 5.0625. To get rid of the 4th power, I'm going to take the 4th root. So I get b is equal to 3 over 2, or you could rewrite it as 1.5. Same number. So right now I have y is equal to a times 3 over 2 to the x. I'll use the one in pink because that's a nice positive exponent. 9 over 2 is equal to a 3 over 2 squared. Well, 3 over 2 squared is 9 over 4 times a. I was taught a long time ago that I don't divide by fractions, I multiply by reciprocals. What I do to one side, I do to the other. I notice the 9's cancels, the 9's and 4's all cancel. And I get a is 4 over 2, or just 2. So my equation is 2 times 3 over 2 to the x, or if you want to say 2 times 1.5 to the x, it's all the same to me. Again, more practice of writing equations just given 2 points, and this time you can write either a linear equation or an exponential. We'll do the exponential first. I don't have the y-intercept, so I do have to do the system, where I have to put the higher x on top. A times b to the third is equal to 24, over 6 equals a times b to the first. I divide out. The a's cancel out. 24 over 6 is 4 is equal to b squared when I subtract exponents, so I get b is equal to 2. So y equals a times 2 to the x. And I think I'm going to use the 1/6. 6 is equal to a times 2 to the first. Well, 2 to the first is just 2. I get as a equals 3, so y equals 3 times 2 to the x is the equation of those 2 points for an exponential. Now to do a linear function, I could use either form. My slope is just change in y over change in x. 24 minus 6 over 3 minus 1. 18 over 2. My slope is 9. And you can do as y is equal to 9, x minus 1 plus 6 is one way to do it. If you want to clean it up a little bit, well, this would be 9x minus 9 plus 6. Or you could do y equals 9x minus 3. They're both the same to me. Well, now let's compare these equations to these graphs, and we should be able to figure out which each graph is. Well, everyone has y equals a times b to the x, and I can see 10, 10, 20, 30, 30, 30 are the a values or the y-intercepts. So I bet you this one is 10, this one is 20, this one is 30. The only one that has 20 in it is c, so I'm going to follow that up, and that one is right here. Graph number 2 is c. I do see that 2 of them have 10 in them. Graph 1 and graph 2 both start at y equals 10, but we have a 1.2 and a 1.5, 1.2 and a 1.5 for my b values, and the closer you are to 1, the flatter you are. So this has to be equation A, and this has to be equation B, because 1.5 is definitely going to be a steeper graph, or better yet, 1.2 is the flatter graph because it's closer to 1. At 30, I have these last 3 that all have 30. Well, out of these 3 graphs that are left, one's growth, 2 are decay. F is the only one that is growing. So now I have these 2 decay ones. I have 30 times 0.85 to the x and 30 times 0.95 to the x. 0.95 is closer to 1 than 0.85. So graph 5 has to be E, because the closer you are to 1, the flatter the graph it is. And then finally, this has to be graph D.